In this lesson, we're going to look at our rational functions. And a rational function, they're simply quotients of polynomial functions. It's a polynomial where it's a function where both your numerator and your denominator are polynomial functions. And as we learned earlier, polynomial function is the sum or difference of monomials, and a monomial is a number, a variable, or the product of numbers and variables. And so we've looked at what polynomials were, and now we're going to look at when we're dividing polynomials. Now, the domain of a rational polynomial function is the set of all real numbers. And when we talked about our polynomials, the domain was the set of all real numbers, except for two things. That was where your denominator was 0, or where you had a radical. Well, we're not going to deal with any radicals, so here we're going to have it's a set of all real numbers except the value of x that makes the denominator 0. So let's look at some polynomials and figure up what their domains would be. If we have the rational function f of x is equal to x squared minus 9 over x minus 3. Okay, here we have a rational polynomial function. Our numerator is a polynomial. Our denominator is a polynomial. So our domain is the set of all real numbers except the value that would make that denominator 0. So we know that x minus 3 cannot equal 0. So that means x cannot equal 3. So we have to eliminate 3 from our domain. So our domain would be from negative infinity to 3, and from 3 to positive infinity. So we've eliminated 3. If we had the rational function, f of x equals x over x squared minus 9. Well, in this case, x squared minus 9 cannot equal 9, or x squared cannot equal 9, and so x cannot equal plus or minus the square root of 9. I'm thinking of my answer. So the square root of 9. So x cannot equal plus or minus 3. Now, when we write that in our interval notation, if you just need to remember, what we're basically saying is we can't be negative 3 and we can't be positive 3. So we're from negative infinity to negative 3. From negative 3 to positive 3, and from positive 3 to positive infinity. So that's how we write it in interval notation, that we're not including plus or minus 3. Sometimes what you're asked is, what do you have to exclude from the domain? When we looked at solving our rational functions, then we just looked at what we had to exclude from the domain. Here we're looking for what we include in the domain. So this is what we include, this is what we exclude. So you just need to read your question carefully to know how you're to write your answer. And let's look at one more. F of x is equal to x plus 3 over x squared plus 9. Okay, in this case, our denominator cannot be 0, so that means that x squared plus 9 cannot equal 0. So x squared cannot equal negative 9. And if we took the square root of both sides, we're going to say it can't equal plus or minus the square root of negative 9. Well, that's not going to give us a real number. So in this case, x cannot equal, we're saying it can't equal plus or minus 3i. That's not a real number. so we can't exclude it. So our domain in this case is going to be from negative infinity to positive infinity. It's all real numbers. There's nothing that will make that denominator 0. And you could reason that through, because whenever you square a number, whether it's positive or negative, when you square it, you get a positive number. And then you're adding 9 to it, so you're going to have a positive number. There's no way that denominator could ever be 0. Okay, so that's how we go about figuring up our domain. Now, we're going to look at a couple of special functions, of rational functions, and look at some things that end up happening with our rational functions. And so let's look at this one. This one is called our reciprocal function. Okay, our reciprocal function. And let's write that again. I think I misspelled it. Okay, reciprocal. Now, there's two rational functions that we can graph by transformations. We won't do a lot of graphing by transformations here because most of them aren't conducive to doing that. But there are two, and we'll look at that just a little bit later in the lesson, of graphing these two functions by transformation. One of those functions is the reciprocal function. So f of x is equal to 1 over x. But right now we want to graph this and just look at some of the things that are going to happen as we go through. Now we know that we can't have 0 in our domain, so our domain is going to be from negative infinity to 0 and from 0 to positive infinity. We cannot include 0. So what we want to do is we want to look and see, well, what's happening as our graph gets close to 0 then? Since we can't include it, what's our graph doing? So we're going to just plot some points as our values of x get close to 0. As you move on into calculus, then this will be called the limit process. As one number is approaching another number, then what's the y value doing? As x is getting close to a number, what's the y doing? But we're just going to look at it with a few points. Now, one of the things that we can notice too is this function is going to be symmetrical about the origin. If we took our function and we substituted in negative x, remember we have our test for finding the symmetry, then what we end up with is the opposite of 1 over x. So we did not get the same function. If we'd gotten the same function that we started with, it would be symmetrical about the y-axis. If we get the opposite function, it's symmetrical about the origin. So this one's going to be symmetrical about the origin. So if I look at my numbers on one side, then I know that if I use the opposite x, I get the opposite y. And so I don't have to actually pick numbers on both sides. I'm going to look at getting close to x. I'm just going to come from the negative side. So I'm going to use negative 1. Then I'm going to get a little closer to 0, so I'm going to use negative 1/10. I want to get a little closer, so I'm going to use negative 100 and then negative 1,000. I'm just going to keep getting closer to 0. Now, if I plug that into my function, I have 1 over negative 1, which is negative 1. If I plug 1/10, I have 1 over negative 1/10, which if you just think about it, that's the same as 1 divided by 1/10, negative 1/10. Here, fractions to me are just a little bit easier because to divide by a fraction, you multiply by the reciprocal. So that's going to be negative 10. Let me just take that off. So that's going to be negative 10. If we did the same thing and we divided by negative 100, then that's going to be negative 100. and this one's going to be negative 1,000. So at negative 1, I'm at negative 1. At negative 1/10, which gets closer, I'm at negative 10. I'm at negative 100 and negative 1,000. So you can see what's happening is my graph is getting closer and closer to where x is 0, but it can't ever be 0 because that's not in our domain. Which then what that tells us is that our y-axis, or where x equals 0, is an asymptote. It's what we would call a vertical asymptote. Our graph is getting closer and closer to it, but it's never going to be that value. So we have our asymptote there. Now we said that this was symmetrical about the origin, so that means when x is positive 1, y is positive 1. When x is 1/10, y is a positive 10, then a positive 100, and so we're doing the same thing, except we're going in the positive direction. Now I talked about that this gets into an idea of limits, but we have some special ways of writing this down. What we would say here as x approaches 0. Now we did it where we came from the negative side and it went toward negative infinity, but if we're approaching 0 from the positive side, it's going toward positive infinity. So when we put this notation, we have to put in something so that people know, well, which side are you coming from? So if we're coming from the left side, here we're coming from the left side, we're getting closer and closer to 0 from the left. What we do is we put a little negative sign above the 0 and to the right. So this is saying we're approaching 0 from the left, not necessarily from the negative, because we could use this and talk about approaching, positive 3. And we could still talk about from the left and from the right. So that means we're coming from the left. As x is approaching 0 from the left, then we want to know what our y value is doing. So f of x is approaching, and in this case, it's approaching negative infinity. We can talk on the other one as x is approaching 0, and we're coming from the right side, so what we put there is a plus sign. Then f of x is approaching positive infinity. Now, one of the things that we're going to find is whenever we have a vertical asymptote, our graph will always be approaching infinity in one direction. That's what happens at a positive asymptote, or at a vertical asymptote. Your graph goes toward infinity. What we'll also say is that it's decreasing without bound, or it's increasing without bound. Now, that tells us what we're doing as we got close to 0. But now we want to know, well, what are we doing as we go out here? As x gets smaller and smaller, what's our graph doing? And the same thing on the other side. As x gets bigger and bigger, what's our graph doing? So as x is going toward infinity, negative infinity, we want to see, well, what's happening? We want to know, well, when x approaches negative infinity. Now, you can only approach negative infinity from one side. So we don't have to put from the positive or the negative. If we're approaching negative infinity, we have to be going to the left. We want to know, well, what's our function doing? And as x is approaching positive infinity, what's our function doing? So let's again pick some points. And in this case, I'm just going to do it on the positive side. It doesn't really matter which side we pick since we know that we're symmetrical. But let's just make us a chart. So as x gets bigger and bigger, we already know what it is at 1. So let's try 10, 100, 1,000. So as x is getting bigger and bigger, well, what your y is 1/10, 100th, and 1,000. So as my x gets bigger and bigger, my y is getting smaller. Now, my y will never be 0. The only way a fraction can be 0 is if the numerator is 0. That's the only way that you can end up with 0, and our fraction here can never be 0 because our numerator is 1. So as x gets bigger and bigger and bigger, then our y value is getting smaller. It's approaching 0. So f of x is approaching 0. So our graph is doing this and this. Now what that makes then is our x-axis is a horizontal asymptote. Our graph is approaching it, but never touching it. Okay, we said when you have a vertical asymptote, your graph is always increasing or decreasing without bound. It's always going to positive or negative infinity. Horizontal asymptotes are always approaching a number, and just a specific number. So what we're going to do in this lesson is we're going to look at, well, how do we find those vertical asymptotes and how do we find those horizontal asymptotes so that we can have a better idea of what our graph is doing. And we're also going to find out that there are sometimes what we call slant asymptotes. And so we'll look at how to find those. So let's look first of all at how we find a vertical asymptote. Okay, to locate our vertical asymptotes, if f of x is equal to p of x divided by q of x is a rational function, and, that should be an and there, and the p of x and q of x have no common factors, and a is a 0 of q of x, then x equals a is a vertical asymptote. Now, this is what that's saying in a little bit simpler words. Let's just take one. F of x is equal to x over x squared minus 1. Okay, we have a rational polynomial function, and p of x, our numerator, and our denominator have no common factors. Now, to be common factors, then that means we should factor that denominator so that our denominator factors, it's the difference of squares, to be x minus 1, x plus 1. And so to be common factors, it has to be the whole thing in parentheses. So sometimes people will want to think, well, x is a common factor, but x is not our factor here. X minus 1 is our factor. So we have no common factors. So that's what we're talking about here. Now, a is a 0 of q of x. So that means we're going to take our denominator, set it equal to 0. Well, since we already have it factored, let's just do it in that form. So x equals 1. X equals negative 1. We could have solved it and set it equal to 0 in that form. So these are the zeros, so that means these are our vertical asymptotes. For this graph, we have a vertical asymptote at x equals 1 and x equals negative 1. Okay, if we took our function, let's say that f of x instead was x minus 1 over x squared minus 1. Well, we just factored that denominator, so let's write it again in factored form. X minus 1, x plus 1. Now, if you notice, I went ahead and put that numerator in parentheses. Our order of operations say it's understood to be in parentheses. Normally we don't put it, but I like to when I'm talking about factoring, because when you talk about common factors, it has to be what's inside those parentheses. So right here we have a common factor of x minus 1. You could kind of think of it as we could cancel that, and so this is the only factor we have left. Now we're going to set that equal to 0. So x equals -1 is our vertical asymptote. X equals +1 in this case is not a vertical asymptote. As you move on into calculus, you'll learn that that is called a removable discontinuity. Both of these are discontinuities because when we draw our graph here, we could not draw it without picking up our pencil at x equals 1 and x equals -1. So there's a break in our graph. This one we call a removable discontinuity. There's some things, and actually if you graph it, there's just a hole in your graph. If you graph this on your graphing calculator, it's going to look continuous at x equals 1 unless you zoom out or zoom in on it a whole bunch of times, and then you'll finally see that one little place where there's a break in it. All right, let's look at one more then. So if we have f of x is equal to x minus 1 over x squared plus 1. Now, what we first try to do is to factor this. This one can't be factored. We try to factor this one, and it can't be factored. It's two terms, but that's not the difference of squares. So we have no common factors, and there is no place that our denominator would equal 0. We looked at this one earlier. If you square a negative, any number, you get a positive, and then we've added 1 to it, so we have a bigger positive. So there is no place that this will give us a 0. So in this case, we have no vertical asymptotes. So it's possible to have more than one vertical asymptote, and it's possible that you have a rational polynomial function where you have no vertical asymptotes. So this is how you go about finding your vertical. It's really tied into finding your domain. But every number we eliminate from our domain, we are not vertical asymptotes. Up here, if we were dealing with the domain of this function, our domain, we would have to eliminate both positive and -1. They're not included in the graph. But as far as there being vertical asymptotes, only x minus 1 is a vertical asymptote. Okay, let's look at some things then to help us locate our horizontal asymptotes. And in doing your horizontal asymptotes, it's really tied into the degree of your numerator and denominator, the degree of those polynomials. Now I've abbreviated it here to makes it simpler for me. I don't know that it's super mathematically written, but it helps me remember. Basically, if the degree of my numerator is smaller than the degree of my denominator, and you could word it the other way. If you want to call the denominator bigger than the degree of the numerator, you can. But if they're in that form, then I'm going to have a horizontal asymptote at y equals 0. We looked at one while ago, the reciprocal function, the 1 over x. Here, the degree of my numerator is 0, the degree of my denominator is 1. And so I did have a horizontal asymptote at y equals 0. The idea behind that is if the degree of your numerator is bigger, then it's going to get bigger at a much faster rate than your numerator, no matter what. Even if this is x cubed and this is x to the 4th, this is still going to get a lot larger. And as your denominator gets larger, your overall fraction gets smaller and approaches 0. So that would be one where your horizontal asymptote is 0, no matter what these two numbers are. If the degrees are the same, you have an x squared over an x squared, or an x to the 5th over an x to the 5th. If the degrees are the same, then your horizontal asymptote is going to be the ratio of your leading coefficients. That's the numbers in front of your highest degree. And then if the degree of the numerator is bigger, then there's no horizontal asymptote. That's where your graph will be increasing or decreasing. And it's going to just do that as it goes through. So there's no horizontal asymptote. We will find out later in the lesson that if the degree of your numerator is 1 bigger than your denominator, that's where you're going to have slant asymptotes. And we'll look at that in a separate section. But right now we just want to look at our horizontal. So if we went through and we had the function f of x equals 9x squared over 3x squared plus 1. Okay, we have our rational function. The degree of my numerator is 2, the degree of my denominator is 2. So the degrees are the same. So that means it's going to be the ratio of the leading coefficients, 9 over 3, which reduces down to 3. So I would have a horizontal asymptote through y equals 3. If I have the function 9x over 3x squared plus 1. Well, in this case, the degree of my denominator is bigger, or you can call that one smaller, but it's in this form. The denominator is bigger than the numerator. Then I have a horizontal asymptote at y equals 0. And if we looked at a third one, if I have 9x cubed over 3x squared plus 1, well, the degree of my numerator is bigger than the degree of my denominator, so I have no horizontal asymptote. Now, since it was 1 bigger, we'll find out later and find out how to find that, we will have a slant asymptote. So this is how the two processes you go about finding your vertical asymptotes and your slant asymptotes. So we want to look at some things that will help us as we go through graphing. Before we do that, before we look at graphing just any polynomial function, we do want to take just a little time and look at graphing by transformations. As I mentioned, there's only 2 functions that we can do by transformation, and so we don't do a lot of this, but if we do have it, then it can make some of our things just a little bit easier. So we're going to go through and look just a little bit at some transformations. Okay, we're going to start with the same one that we looked at a while ago. We had f of x equals 1 over x. Now, when we learned to do by transformations in an earlier chapter, if you remember, what we always did is we knew some specific points, and we just took those points and then we shifted them. Whoops, that's not a very straight line. So let's look at this as our graph. And I didn't do it on a little coordinate plane because my points, I'm going to get some fairly small, and I wanted to be able to show those. I wanted to have a little bigger grid. So we're going to look at the points. We're going to do 3 points. We're going to do x equals 1/2, x equals 1, and x equals 2. Now, if you remember, the name of this function is the reciprocal function. So basically what that means is that y is the reciprocal of x. And so that's an easy way then to remember your points. What's the reciprocal of 1/2? Well, 2. The reciprocal of 1 is 1, and the reciprocal of 2 is 1/2. X and y are reciprocals of each other. And you could go through and you could actually, write down 1 over 1/2 and divide by the reciprocal. But if you just go through and think of the name, this is what we mean by reciprocal on your calculator. That's the reciprocal key a lot of times. And so it's the reciprocal. Your points are reciprocals of each other. So at 1/2, we're at 2. At 1, we're at 1. And at 2, we're at 1/2. Now we know from what we did earlier that this is going toward positive infinity, and this one is going toward 0. Didn't get that very straight. This one, if we graphed it, we know also that it was symmetrical about the origin. So at negative 1/2, we're at negative 2. At negative 1, we're at positive 1. And at negative 2, we're at 1/2. And so our graph is doing something along this line and going on down. Now, that's what we would call the parent function. That's basically what it looks like. So if we were going to do transformations, we would do them in the same way that we did when we did all of our transformations. If we have f of x equals 1 over x minus 2. Now remember, whatever's with your x, in the parentheses with your x, and that's understood to be in parentheses, that affects your x value, and we undo it. So that means we would add 2. So what we would be doing with our graph here is we would be taking each of these points and moving it to the right 2. So we would have our point 2, 1, 2, 1, 2. And we would still have our function. We still have the same horizontal asymptote. Whoops, that needs to go down a little bit straighter because we now know we have our vertical asymptote at x equals 2. We would take our points, we would go 1, 2, which would actually be about here. One, 2, and 1, 2. So we just shifted our graph to the right 2 units. If we had f of x equals x minus 2 plus 1. Now see, this is outside of our parent function. So this affects the y value, so that means that after we shifted it, then we would go up 1. So we took this point, we shifted it, and now we would go up 1 unit. So that would change our horizontal asymptote. It would now be at 1. If we took this point, we would go up 1 unit. And we would go up 1 unit. And so we would have our graph. We would take all these points and go up a unit. And then the 1/2 would be up here. And we would have our horizontal asymptote at y equals 1. And our vertical asymptote then would be at x equals 2. So it's doing the same type of transformations that we did before. You just have to know your parent function. So these are the points that we use. We use reciprocal points. Now the other one that we can do by transformation is f of x equals 1 over x squared, if it's in that form. And again, even with these, we're going to look at, when we look at how to graph our rational functions, we're going to be able to graph even these very simply. And so if you didn't want to work with the transformations, you didn't have to, but it helps you in creating functions, understanding your transformations. So if we look at these points, the ones we're going to use, this just means that we're going to be squaring x. So let's use the points 4, or excuse me, let's go through. Okay, we're going to go through. We're going to use the same points that we did. We're going to use 1/2, 1, and 2. So we're going to pick the same points that we picked with our reciprocal function. The only difference is here, and we're going to square that answer. So this 1/2 squared, we would do that first. So 1/2 squared is 1/4, and then we would want the reciprocal of it. So it would be 4. 1 squared is 1, the reciprocal is 1. 2 squared is 4. The reciprocal is 1/4. So it's just going to change our y values as we go through and do that. And so our graph, now, this one is not symmetrical about the origin. It's symmetrical about the y-axis, because if we substitute it in negative x, we have 1 over negative x squared, which would give us 1 over x squared. We get the same function. So this has y-axis symmetry. So I picked the points 1/2, 1, and 2. At 1/2, I was at 4. At 1, I was at 1. And at 2, I was 1/4. So my graph would be going up. Then at negative 1/2, I would still be at positive 4. At negative 1, I would be at 1. And at negative 2, I would be at positive 1/4. So instead of it being symmetrical about the origin, we're symmetrical about the y-axis. And then all those same things happen as you go through and you do your transformations. So if we had f of x equaled 1 over x plus 1 squared. Okay, we undo our x, so that means we would have to subtract 1, so we're going to move all of our points 1 unit to the left. So we've got this point, this one, and this one. So that graph then would be going up. Notice what it did is it changed our vertical asymptote to being at negative 1. Then we would move this one 1 unit to the left. It was 1/2. And so we have our new function. But we do all of those same things. If we had a number out here plus 5, then we would move all of our points up 5 units. It would affect the x. You don't get very technical ones or involved ones with your rational. Once they start getting involved, we'll use some different techniques. So in the next lesson, what we're going to do is we're then going to look at how to graph using our vertical and horizontal asymptotes. And we're going to look at how to do our slant asymptotes. So in the next lesson, we'll look at our graphing.